Crikey, didn't see you there, mate. Shh, you'll scare the light away. It's okay if I talk because they're attracted to my natural Australian accent. Today, watch as I take an elite team to observe wild radiation in the wild. Let's start our journey by talking about microwaves. I'll use an example that you're all familiar with, microwave oven. Have you ever wondered why it's so easy to microwave water when it has a high specific heat? Well, that's because water's polar, and when microwaves move through water, they create different fields. And since water is polar, it attracts to different fields, and that makes it jiggle around. And when it jiggles around, that creates heat. So that's why your food gets warmer. I'll show you right now with a real-life example, a real-life microwave oven. Let's go! When the water in the marshmallow heats up, that heats up the surrounding gases, which are trapped in pockets all around the marshmallow. And because of gas laws, this makes it expand. You've probably seen delightful videos on the interwebs of people foolishly putting metal into microwaves. The reason why this is a bad idea is because metal tends to reflect microwave radiation, unlike food with water, which tends to absorb it. When all of it is reflected, it just bounces all around the microwave until it could eventually damage something important, like the magnetometer inside a microwave. And when that happens, fires can start, and homes can easily be lost. That was a great shot. Now everyone will know the dangers of putting metal in a microwave, and hopefully none of them will do that. This? My dingo senses are tingling. No! You can't put metal in a microwave! Oh, crikey! Just a bad dream. Because that's not actually what happens when you put metal in a microwave. It just sparks around a little bit. Oh well, time for breakfast. Let's go! Oh, crikey! Didn't see you there. Next up is my twin brother Alan, and he's going to talk to you about visible light.
Visible light is the reason you can see stuff like this video. It is the only part of the electromagnetic radiation spectrum that you can see with your eyes. It is located between infrared and ultraviolet radiation, ranging from 400 to 700 nanometers. Each color has a different wavelength, with violet being the shortest and red being the longest. In order to perceive this spectrum, cell-shaped cones in our eyes act as receivers tuned at the specific visible light wavelengths, making our eyes able to differentiate between each color. Now I will show you a creative demonstration.
As you can see from this bright pink costume, most wavelengths of light will be absorbed by the costume, but the pink wavelengths bounce back, which is then perceived by our eyes.
Oh, crikey! Didn't see you there. Next up's my other twin brother Nathaniel. He's going to talk about ultraviolet radiation. Should be a blast. Let's go!
Hey there, I was just here to observe some ultraviolet radiation from the sun. Ah! That really hurt. Ultraviolet radiation ranges from 400 nanometers to 100 nanometers in the electromagnetic spectrum. It is divided into three sections. The near ultraviolet, which has the least amount of energy, the far ultraviolet, which has the middle, and extreme ultraviolet, which has the most. Ultraviolet radiation has more energy than microwaves and visible light due to its higher frequency. This enables it to knock off electrons off atoms, causing detriments such as cell damage and DNA mutation. Ultraviolet light wavelengths can be divided into three different sections, which may or may not be filtered by our ozone layer. As you can see, I'm the ozone layer, and Alan here is the UV C and B rays. He has too much energy, so I can block him. Oh no, it's a UVA ray! That's too little energy!
Crikey! Oh, crikey, didn't see you there. When this little dingo wakes up, we're going to learn about X-rays. But until then, shh, he's sleeping.
X-ray, which is short for X-radiation, has more energy and a shorter wavelength than, say, for example, ultraviolet. It is because of this high energy, it is actually able to knock electrons off of an atom, which ionizes the atom and can make it very dangerous for a human or any living thing, which is why coming into contact with X-rays is dangerous. Now, X-rays are divided into two major groups, soft X-rays and hard X-rays. both of which encompass between about 10 nanometers to 0.01 nanometers of wavelength. Soft X-rays are used for things such as X-ray crystallography, which determines the 3D structure of a crystal, and X-ray microscopy, which is used to find really small objects that a regular microscope can't pick up. Hard X-rays are more commonly used in medical purposes and things like that, as they are able to pierce through. Say, for example, that this is a visible light photon. If I throw it in to the pool, it's not able to go underneath the surface. Yet, if I were to take an X-ray, because of its shorter wavelength, it's able to go right through until it hits something more solid, such as the bottom of the pool.
Oh, crikey, didn't see you there. Well, now you all know about light. See you next time.